Well, this is the next video in the Arduino security panel/system series. In this video, I'm going to go over the mainboard, which contains the first 8 zones, 4 outputs, and a siren output, plus the RS-485 LAN for communicating between the different parts of the system. Now, a few design considerations. So I've decided that I will use RS-485 signaling between all components of the system, and that the way it will be set up, that basically all boards listen on the bus, and then when a device changes to send and requests to speak to the devices, the various devices will listen to the data on the line. Reasoning for doing this is that a lot of security panels these days are built like this, where a lot of the integral components like keypads, zone expanders, relay expanders, even communications interfaces like IP interface are on an RS-485 LAN. And due to the MAX 485 RS-485 half duplex communications chip, I can have the necessary two-way communication as required between the various items. So in this video, I'm going to go over the mainboard, the method behind the design, and basically what's done to try and detect each of the different values on the zone inputs. I've how to utilize some shift registers, like I said, and also op amps to allow for conversion between different voltage levels, as the Arduino doesn't expect anything higher than a 5-volt signal, but a lot of security devices work on 12 volt. So here we are in the schematic of the mainboard. Now, the section we're looking at here mainly, this is the microcontroller here. As you can see, I've got these 3 lines here that are basically goes to the shift register, which provides all the necessary zone inputs per se. We have outputs directly controlled by the actual microcontroller because the pins were available. I was able to control these outputs independently, which includes the output for the siren, which creates an audible noise to indicate that's an alarm condition. These 3 pins here are basically used as what I call a device ID. So basically, depending on which of these pins are grounded, depends or tied high, tells the microcontroller what kind of device it is. So in this one being the mainboard, its default is tied low and it can't be changed. The mainboard will always be device 0. Stuff like keypads, zone expanders, relay expanders will have different device IDs, which should be configured via a soldering pad. And this is done on manufacture to make sure it can't be changed easily, and to ensure that no miscommunication occurs. These 2 pins here would also then be utilized with those 3 to indicate if there's more than one of that device there. So for example, we have a zone expander. I can have up to 3 more zone expanders, so that allows for another 3 lots of 8 zones being added into the system, which communicate on the RS-485 bus to provide additional zone inputs, which can then be used to run additional security devices. But also these same pins can also be used to identify if it's how many of the relay expanders. So basically, these 2 pins will define whether or not you've got relay expander 1, 2, or 3, or zone expander 1, 2, or 3, or keypad 1, 2, or 3. These pins will not be used for a LAN interface, or I'm actually going to make the PSTN separate to the mainboard. I was going to integrate it, but due to the limitations of the ATmega328, I've decided to make it as a separate device. So these won't need to utilize the individual identification of how many there are in the system, because you only will ever have 1 in the system. And because of using 3 bits for the device IDs, it means that I can have up to 7 different types of bus device. Now, this does limit the system, but then again, the ATmega328 is a limited microcontroller. If I do end up revising this project with say like a 32-bit microcontroller where there are more pins available, and I have a lot more available, then yes, I may look at an updated version of this. For the time being, this is just a simple security system based around current design and current security system methodologies. As you can see here, I'm using an LM358DT dual op amp. So what this does, it takes the 12 volt input first, it buffers it so it doesn't affect the voltage reading from the end of line resistors, and then runs it through a voltage divider buffer again, bringing the voltage level down between 0 to 5 volts to detect whether it's in an alarm, tamper, or sealed condition. Here is the 485 chip. Basically, this allows the RS485 signaling and allows everything to communicate. Of course, we've got the shift register here, which gives us our 8 zone connections, and of course an SPI programming header. Now, on the main board, the main board will contain the main power. Like with all security systems, the main power is on the board. Now, I've decided to go with 24 volt AC for the power supply that it uses, which goes obviously through a rectifier and then comes out unregulated. It then feeds into 2 switch mode chips, an LM2576, a 5 volt and 12 volt version. Now, these do provide up to 3 amps of output. That is probably overkill for what I require. Now, the reason I've chosen this is that it keeps the componentry simple. Because they're voltage specific, they all, as you can see here, they both use the same output components. This makes it easier for me to buy the components. It keeps things simple. Otherwise, yes, I would choose a different 5 volt regulator. So on all the sub-series devices, I'll probably have the 5 volt regulator, but the main board will only be the one having a 12 volt regulator because it takes the 12 volt AC and regulates it out to 12 volt DC with up to 3 amps of current. And generally speaking, that is actually double what is normally provided to panels in the industry. Normally, most panels don't need any more than 1.7 amps on the 12 volt outputs to run the various devices and stuff like that. But like I said again, in the interest of cost and simplicity, I've gone with this type of switch mode chip. And the other reason for choosing 12 volt AC is that there's a lot of security power supplies out there that are either 16 volt or 24 volt. Now, I will say this. This board, because of the design, can take a 16 volt AC supply as well as a 24 volt, but I would generally recommend use the 24 volt AC as per my design, but it will take a 16 volt AC supply as well. Now here, these MOSFETs allow for the necessary multiplexing of the inputs. I'm only using one ADC and multiple zone checks. So the first 8 here are here. So what these do is that when the microcontroller sends a value into the shift register to fire up zone 1 will then turn on, and it will allow 12 volts to flow from the 12 volt line through the end of the line resistors and then come back to the MOSFET, and then through the MOSFET into the op amps, and then of course into the ADC to determine what condition the alarm is in. With the driving of the outputs, as it's just a negative side switching, it's like with the siren and the 4 utility outputs, you basically have one side connect directly to the 12 volts, hence why there's an extra 12 volt connection on the screw terminals. You then have the negative side connected to the utility output, which is technically an input. And then pretty much when that output fires, it connects that side to ground, allowing that device to act, because most security devices are 12 volt based, and it's just a matter of just providing power or providing connection to ground. Now, I decided to, as another design consideration, that I'm not going to put any physical mechanical relays on this board, similar to what Paradox does. They just give you a series of outputs that basically pull to ground. And what you would have to do is, if you want to say, per se, you want to have like an actual relay output for, say, controlling a door and stuff like that, you can buy them from almost all security suppliers. You can basically put a relay in. that is has its coil energized by the 12-volt utility output loop, and then it provides the switching between normally closed and normally open type facility that you'll normally use in that regard. And furthermore, with the siren, again, a lot of sirens these days and alarm systems are piezo based, so therefore they just require 12 volts. So again, the 12 volt sides connect directly to 12 volts, and the negative sides connect to the siren output. And pretty much the moment that the gate is charged and provides connection to ground, bang, the piezo starts to sound. There obviously will be a time on that because you can't have a alarm siren going for any longer than 5 minutes in Australia. And these are just various connections. So on this, so we got the first four there, which you use your data bus. Then you got the 8 zone inputs. Of course, then there's the siren with its supply, and of course the 4 outputs. So here's the main board for the Arduino security system. As you can see, designed by me and obviously attached to my channel. All this here is to do with the power supply. So provide 5-volt power, 12-volt power for all your devices, and then basically the main stuff is here. A lot smaller, because beauty of surface mount is you can do it quite small. And as per the image I showed when discussing the RISCO system, all your connections are down the bottom here. So we've got 12-volt ground, A and B bus, and then of course then the zone inputs, siren output, and then your utility outputs. You got your AC in here on this side, and the reason it's put there instead of on the other side like it is with some panels, it's more or less a component arrangement. And also right in the middle here is the SPI programming header. So when the unit is initially programmed with its firmware, it will be done through SPI. Now, another design consideration I'm done is that with RISCO, like I'm going to do the same thing as they do, is that every single board that works in the system on the RS485 bus all have the same firmware. They basically have the same firmware and they all run the same controllers. So that's what I'm doing here. But the way it differentiates is that device ID I pointed out when discussing the schematic. The device ID tells the firmware which part of the firmware routines it's going to run, whether it's a mainboard, a keypad, a zone expander, relay expander, IP interface, PSTN interface, you name it. Those pins tell it what code to run. And that's the beauty of the ATmega328. Very useful, very versatile. And as you can see, the actual just circuitry itself is only a small area. The majority is the power supply. Now, I could have put the power supply onto a separate board of its own, but realistically speaking, I took a page again out of other panels that I've worked on. They have the main power supply on the main panel, and then basically everything's powered from that one panel. Basically, it sends the power down the various cables. So basically, the RS485 bus here, which connects keypad and stuff, etc. It also provides the power to any other ancillary components down the line, basically. And as you can see, the MOSFETs are used to switch on and read the various outputs. And basically, in my case, I will use dual end-alone resistors. It's how the code will be programmed. The code is going to be open source, so if people want to add in functionality like support for other resistor types, I'm going to go down the path of what was used in the concept system, which is a pair of 10K resistors. It means it keeps the amount of current draw to a minimum, and it provides very clear, distinct voltage levels to detect for various conditions. The 2 resistors together, they call it 4-state monitoring. I technically call it 3-state because there's only really 3 states you want to know about, and that's basically short circuit, sealed, and unsealed. Open circuit is, you get that as default, but like I said, so I call it 3-state monitoring, they call it 4-state monitoring, tomato, but basically you're looking for a short circuit condition, a sealed condition, and unsealed condition. And the reason for this is to make sure that that no one tampers with the devices in the system, so that if someone does tamper with it and triggers a tamper, it will immediately alarm the system even though it's not armed, because the tamper is always in a armed state. Now, the board itself is relatively small compared to some actual alarm system panel boards these days, because this is a fairly simple system. If the series proves to be popular, I may look at doing a more advanced security system from my knowledge of what I've worked with. I may actually look at putting actual relays on board and obviously allowing for extra power supply as required. But for now, this is the main board. In the next video, I'll go over the keypad design, because the keypad is what's used to program the system and set values. Yes, the initial program is done through the SPI through Arduino, but because all the security systems are designed, a lot of programming is through the keypad, just to basically set the various flags and settings to indicate what the system's to respond to, and also how to, trigger an arm and disarm on the system, basically. But I'll see you in the next one.